The plasma-electrolytic oxidation of the metal parts surfaces is an effective means of protecting them from corrosion, overheating, and mechanical overloads. When you obtain oxide coating of steel parts, firstly, a layer of aluminum is applied to the working surface, then it oxidized and mechanically processed with cutting or abrasive tools. So in both cases, we have the issue of interaction of hard indenter with oxide components of the homogeneous coating. And the purpose of the presented study is to analyze the stress state and strengths of oxide ceramic coating under the action of abrasive particles. For the method of formation of construction of aluminum ceramic coating are well described in technical literature, but the issue of strengths of layer composition under local load has been studied not so much, which led us to this research. Although the main feature of this study is the use of one-dimensional mechanical model of interaction of non-homogeneous coating with hard abrasive proposed by the authors that allow us to obtain a result in an analytical form. So let us consider a rigid structure element foundation on which a thin coating is applied, consisted of an outer hard, functionally gradient part or layer and relatively soft, non-homogeneous substrate, as it is shown in Figure 1. The mechanical contact between layers is considered as ideal. From mechanical point of view, the hard outer layer is considered as a non-uniform elastic plate, which works for tension and bending, and the soft inner layer is subjected to the Winkler hypothesis of proportionality of stresses and elastic displacement. To simulate contact with a sliding abrasive particle, the structure is loaded by a vertical force P and a horizontal friction force Fp, uniformly distributed along z-axis deep in the drawing. In the presented model, large values of friction coefficient F correspond to sliding of fixed abrasive in micro-cutting process, and small values of F friction coefficient correspond to the sliding of the unfixed abrasive with possible rolling. In addition, we assume that the structure is under plane strain condition. It is necessary to study the stress distribution of the non-homogeneous coating and establish the level of the safety margin. Under the accepted assumptions, we can write the equilibrium of hard part piecewise homogeneous coating on a soft elastic foundation with fading boundary condition for forces and moments at the infinity that stand for equation 1 and 2. We have the boundary value problem 1 and 2 that describes the unknown fields on vertical displacement of hard coating on an elastic foundation. The variable parameters of that contains equation 1 and 2 in this case are expressed by the integrals as it is shown on slide number 4. Here it's worth noting that integrals of the coating thickness are calculated with the piecewise constant function that contains the mechanical characteristic of the coating layers. After calculation the integral mechanical characteristics, the solution of problem 1 and 2 was obtained as follows. Displacement of natural surface of the hard functional gradient coating, equation 3, tension, force and bending moments in the coating, equation 4, contact stresses on the coating interface, equation 5. And the stress through the entire thickness of the functional gradient coating obtained as piecewise function, equation 6. The strength of coating is evaluated according to the von Mises criterion. So now the obtained results make it possible to determine the value of the allowable load, and which depends on the mechanical and geometric characteristics. For the simulation of the behavior of functional gradient coating, we used a linear approximation for mechanical characteristic distribution over the thickness for the hard part of coating, and the linear and piecewise distribution for soft substrate. Because in the case of ceramic layer obtained by plasma electrolytic oxidation of the duralumin alloy, a thin annealed aluminum appears under the oxide layer. The mechanical properties of the functional gradient coating materials and the layers thicknesses are given in the table 1. Distribution of mechanical characteristics of the thickness of the coating are shown in figure 2. On slide 9, we have the result of evaluation of the equivalent stress, safety factor, and normalized equivalent stress in the functional gradient coating with unfixed abrasive. We made calculation with small value of friction coefficient. And next slide present the similar result for the bigger friction coefficient. As we see in figure 3 and 4, the stress state is concentrated in the vicinity of the line of application of the local load, and the highest level of the equivalent stress is observed in the case of fixed abrasive. Also, since we have a non-homogeneous coating, we should also take into account the special distribution of strength characteristic, and in this case the value of the yield limits of each layer. Therefore, the more correct determination of limit state of layer coating is given by the distribution of safety factor or normalized equivalent stress. So let me read the conclusions. The developed calculation technique makes it possible to investigate in an analytic form the influence of mechanical and geometric characteristics of the functional gradient coating on its stress state and limit equilibrium under an arbitrarily oriented local load. Using the accepted model and an example of linear approximation of functional gradient ceramic coating on the piecewise homogeneous substrate. The interaction of the coating with fixed and unfixed abrasive was investigated. It is shown that equivalent level of equivalent stresses in the case of interaction of functional gradient coating with a fixed abrasive is higher than for unfixed abrasive, making this, as expected, more dangerous. In addition, some other problems that the functional gradient coating under local load, under center configuration, geometry, and mechanical properties, it was observed that the ultimate state of functional gradient coating can be achieved not on the place of the maximum equivalent stress, but at the place of the minimum of safety factor. Thank you for your attention.